Hello guys, welcome to another interesting session of our DSA course of My Project Ideas. Today's topic is gonna be fun and it's gonna be the last of the asymptotic notations that we have already learned. So today we are going to learn about theta notation. So brace yourselves, gear up as we are proceeding towards learning the last asymptotic notation. We will be looking the theta notation in a very detailed way. If you have no knowledge, no worries. We'll cover from the basic layman terms to the advanced level. And if you have not looked at the previous lectures, I will recommend you please go through the previous lectures. Otherwise, this topic is gonna be a bit tough for you. Okay, so let's start. So let's look at the functional representation as we do in all the other asymptotic notations. So what we are going to do is we have g and f to be the function from a set of natural number to itself. So the function f is said to be theta of g if there are certain constants c1 and c2 which are greater than 0 and a natural number n naught such that c1 of into g of n is less than equal to fn is less than equal to c2 into g of n for all n is greater than equal to n naught. So it sounded a bit tough, I know. So okay, the mathematical representation is better when we look it in the set builder form. Then we get to understand it in a better way. So let's look into the mathematical representation and let's make it a bit simpler for you guys. So here it's written theta g of n is equal to f of n such that there will be existing certain positive constants say c1 and c2 and n naught such that this part is n naught, it's not only 0, so n naught is less than equal to c1 into g of n is less than equal to fn is less than equal to c2 into g of n. So I already explained you in the theory of the asymptotic notations that the theta basically bounds between two limits, that is both the lower limit and the upper limit. So see, the functions are bounded. I bet. Let's go back. The functions are bounded inside a limit. There is a limit to the upper limit also, the upper bound also, and there is a limit to the lower bound also. So your function has a limit between two limits or between two possible types. Your function cannot go above a certain limit or your function cannot be less than a certain limit. We looked on the big O notation, the omega notation. So they're only one part, the upper or the lower part, they were restricted, but here both the ends are restricted. Okay, so what does the above definition means? That if fn is theta of gn, then the value of fn is always between c1 into gn and c2 into gn for large values of n. So always the value of fn will lie between c1 into gn and c2 into gn. Okay. For all n will be greater than equal to n naught. What's n naught? N naught is a positive constant. Okay. Now let's look at the graphical representation. Here you can see the fn wala curve is here, and the fn function always lie between c1 into gn and c2 into gn for all n, because this part is n naught and right side of this will be n. So for all n greater than equal to n naught. Got it? So let's make it a bit simpler again. In simple language, big theta n, it denotes, this notation specifies asymptotic bounds both upper and lower, which I said you in the previous slides, for a function fn, and it provides the average time complexity of an algorithm. Already explained. Because this puts certain bounds to both the upper and lower level of a function or the lower bounds of a function. So it provides average time complexity of an algorithm. These are the steps you need to follow to find the average time complexity of any program. First, what you need to do, break the program into smaller segments, because a huge program, if you do not break it, it will be not only complicated for you, but also for all other people who are gathering information from your program. Then Find all types and number of inputs and calculate the number of operations they take to be executed. Make sure that the input cases are equally distributed. Then you need to divide these certain input cases into equal segments. Calculate the number of inputs and then you have to divide it into equal number of segments. Okay, easy for calculation. Then do you find out the average? Sum of all the calculated values and divide it by the total number of inputs. Okay. Then, okay, so much of discussion right now. Let's have a look at the code because DSA and coding, it goes hand in hand. If you know all the theory and if you do not know the coding, it's of no use. The ultimate goal of DSA is to optimize your code. So now let's move to the codes. So again, this code I have provided in, I guess, okay, the codes have been provided in your Python. Let's move to the Python compiler for once. And let's write it. So here is my code. Let's run. So see, what does this code has in store for me? First, I write a function whether a key exists in an array or not. Okay, this is a function to find whether a key exists in an array or not using linear search. So you first write a function for the linear search. You have to traverse the given array. Then for element in array, you have to search for an element in array. If the element will be equal to key, then you have to return true or else return false. This is the driver code. Driver code is the main code, the main function. So here you have given an input and you have given a value to be searched. So this element matches the key. So this element is found. So it shows element is present in the array or else element is not present. So basically this is a linear search program. I hope you got it. So why did I tell you about the linear search program? So why is it important here? Here. In a linear search problem, you are assuming that the test cases are uniformly distributed, including the case where the key is absent in the array. So if the key is absent in the array, then also you are assuming that the cases are uniformly distributed. So sum of all the cases where the key is present in position, such a random position, or it is not present and you are dividing by n plus 1. Basically, you are getting the average case. So you are dividing all the possible cases by the total number of cases. So what is the average time complexity? Summation of theta I, that is I is equal to 1 to n plus 1 divided by the total number of observations, that is n plus 1. So when you solve it, just a bit here. When you solve it, when you get through it, when you open it, so how do you add the natural numbers? It's basically what you tell the number of average. How do you find out the average of 1 to n? Sum of the average. What do you do? N into n plus 1 by 2. So here the same thing is done. N plus 1 into n plus 2 by 2 by n plus 1. Okay. So when you again simplify, you get it as theta of 1 plus n by 2. So if you remove all the constants, you get theta of n. So what is the average case complexity, or the if you represent it by the time complexity of this program, it's theta of n. Okay. Then when do we use the big theta notation? Why is it important and in which cases do we use? Big theta notation describes the upper bound of an algorithm's time complexity. I'm sorry, it's big O. So big O notation basically describes the upper bound of an algorithm. I told you that big O always put a restriction on the upper bound, so it describes the upper bound of an algorithm. So it is particularly used for understanding the worst case scenario. We are talking about big O. Big theta notation provides a more precise analysis because it considers both the upper and lower bounds. It gives a tighter estimate of the average time complexity. So theta notation is used there where you need a more precise analysis, where you need to consider both the upper and lower bounds, and it gives you a tighter estimate of the average time complexity. However, finding uniformly distributed inputs can be challenging in practice because what we learned is in an average time complexity thing, we basically divide our input into equal sizes. So that is actually difficult to find uniformly distributed inputs. So therefore, Big O notation is often used due to its simplicity and still valuable insights into performance. So Big O is basically easy because it keeps our describes the upper bound of an algorithm, and we can understand the worst case scenario, which is our ultimate goal. So it's easy. So therefore big O notation is often used, and big theta is not used that efficiently or that properly, because here it is difficult to have a track of the same size of input cases. Average time complexity becomes hard because a lot of mathematical formulations come into account. So I hope you understood the big theta notation, where it is used, why it is used, the graphical annotations, the coding structure. I hope you understood.